Okay. Okay. So, hello everyone. So, this is the third class of this course on electromagnetic theory, and this is a TA class. Basically, this TA-ship is a part of PMRF uh, that we have to do. And I am a PMRF fellow from IISc, and I'm doing my PhD here. So, okay. So in the last two classes, we had, if you remember, we had discussed about the basics of electrostatics, where we talked about Coulomb's law. And then we moved towards Gauss's law, where we saw that how the symmetry in the problem can be used, and it makes calculations and analysis quite simpler. We derived some important relations between, the charge density and the electric field and the concept of potential. Okay, so that's all that we had done in the last class. Now, today, uh, we would be talking about conductors and induced charges. Now, to start with conductors, first we need to think about the fact that when we have any material, now the medium properties of the material, like what is the conductivity, permittivity, all these things are important factors that govern the type of the type of field that would be generated and all that. Okay. So basically, when we are talking about conductors, we need to understand that conductors have free charges. Okay. So in any, suppose a metal is a conductor. So if you take a metal piece and now if you, like, we know that in this metal, there are free electrons and free charges that are moving, right? Now, on the other end, if you have some dielectric, okay, so if you have, suppose, I don't know, suppose rubber or anything, some metal which is not a conductor but has some level of insulation, so it becomes a dielectric. In those cases, again, there will be charges which will move, right? But they are not as free as the conductors. Okay. Now, why it is important is, imagine you have a conductor, okay, and you apply some electric field. Okay. Now, what do you think will happen? Okay. Can I get an answer here? So if you think of any metal piece and you put it in presence of some externally applied field, what do you think will happen in the conductor? Anything, like what is your basic idea? Like what is going to happen? Okay. So any idea, any clue? Some conductor, maybe a metal, okay, some metal, you put it in presence of a electric field, what is going to happen to the conductor? So the very basic thing that one needs to, you know, or the way of answering this question would be that there are some free charges. Now, these charges will experience some force because you have applied a field. It's in presence of some field, so it will experience a force, and therefore they will redistribute. So what it means is, now if you have electrons here, the electrons will get a force in the minus x direction, right? Because they are negatively charged. You have an electric field, so you will have a redistribution and accumulation of charge that will be happening, right? So if I look at it like this, so if there are charges, there will be some redistribution such that you have the electrons moving in this direction, right? Basically, the electrons will move in this direction. So you'll have an accumulation of negative charge here, and that would leave some positive charges at this end, right? So basically, a redistribution of charge is going to happen. Now, if we know about what this is called, this is what polarization is. Basically, now your charge distribution is having a net polarity, right? There is more positive charge here, more negative charge here. Now, what will result from this? So we know that now there's like if we just look at this region, it has a effective positive charge. This has an effective negative charge. So there will be an effective electric field that will be generated in this direction, right? So there'll be an electric field inside the conductor that will initially be generated, right? Now what will happen is this charges will distribute in such a way that all, you know, all the charges will come to the surface of your conductor, such that this electric field will be equal and opposite to the applied field. What will happen in that case? So the net field inside the conductor goes to zero. Okay. So the very fact that if you have a conductor, the field, and you put it in presence of some field, the field inside the conductor is zero, is because of this presence of free charge and because of the fact that the charges can redistribute and form this induced electric field, which is equal in magnitude to the applied field but opposite in direction, right? So clear till here? So what it means is, what is the field inside the conductor? That's what we discussed, right? The field inside the conductor should be zero. Clear till here? Right? This is what we just talked about. So the point is, why is it zero? It could have been some other value, right? So it is because your charges are free to go and get distributed on the surface, such that there is no charge in the bulk. Okay? Because you want a field which is equal and opposite to the applied field. That will be a general tendency, so that it gets cancelled. So that is, the equilibrium condition will be such that they'll try to repel and go towards the opposite direction. And because they are free, they'll all go to the surface. Now, because they'll go to the surface, there'll be no charge, no net charge density in the bulk. Okay. So because there is no charge in the bulk, that also tells us that the field is effectively zero. Okay. So if we want to talk about, from Gauss's law, what this tells us is when we have divergence of E equal to rho by epsilon naught. So in this case, E is zero, rho is also zero, right? So the fact that electric field is zero tells us that there is no charge inside, and vice versa. Now, so whatever charge you put in, okay, so if you suppose put in some charge to the conductor, what will happen? All the charge will go to the surface. Now, once it goes to the surface, what happens there, right? So if you have some electrons on the surface, suppose, right? Now they can also move on the surface, right? But the equilibrium condition will be that there is no such motion. There will be an equilibrium state of configuration of the charges, right? So that means any electric field which can result in a net potential difference along the surface should be zero. Okay. So that tells us that if we have 2 points A and B, okay, within or on the surface of the conductor, okay, then the fact that there should not be any work done at equilibrium, okay, so there should not be any movement of the charges. So this tells us that at that point, VA should be equal to VB, which means that the surface of the conductor is an equipotential surface. Okay. So that because now it's equipotential, this also tells us that there is no tangential component of electric field on the surface of the conductor. So whatever electric field you have, that will always be perpendicular to the surface, so that there is no work done in moving the charge from one point to another. Okay. So electric field is perpendicular to the surface just outside the conductor. Otherwise, charge will immediately flow around the surface until it kills off the tangential component. So at equilibrium, when we're just looking at a conductor, the electric field will always be perpendicular to the surface. Tangential components will be zero. The surface of the conductor will be an equipotential surface, and there will be no charge or no field inside the bulk of the conductor. Okay. So this entire property of conductor is coming because of the fact that you can have redistribution of charges because charges are free when you have a electric field. Okay? Now, based on what we just discussed, if we look at this question, right? So when you have a plus Q charge, this plus Q charge will create a net electric field in this region, right? There'll be field lines radiating outward from here. And then, so there'll be a net field in this region. And there you have put your conductor, right? So for this charge, the electric field direction will be in the positive, like in this direction, right? You will have all these things. So that means the electrons will move opposite to that. So you will have a redistribution of charge, something like that. So you will have a minus here and a plus charge distribution here. So that's how the redistribution will happen, right? So now based on this, we know that the field inside will be 0 and the field outside will obviously will have some value, right? Because you have this charge, so there'll be some field outside, but inside the field will be 0 because of this redistribution. Yeah. Yes. Okay. Now, what happens if you have a conductor like this now, where in this case, it's a hollow conductor. Basically, this is the bulk of the conductor, the gray area, and the white region is a hole, okay? A hollow region inside the conductor. And you put in a charge Q inside this hole, okay? Now, based on our understanding as of now, like talking about electrostatics, Gauss's law, the fact that the field inside the bulk of the conductor is 0, all this information, if we make use of that, can you tell me what the field will be inside this hollow region, okay? And what the field will be in the bulk of the conductor? What will be the field outside? Okay? Any answers? So you have a Q charge in this hole. What will be the field here? Will it be 0 or non-zero? You can also use the chat box to write your answers.
Inside it field is 0, but outside it is normal to the surface.
Okay, so inside meaning, see, there are two regions. One is this hollow region, right? And
Yes.
another is the bulk of the conductor, right? So basically, it's something like this region where you have a hollow region. Here you have put in some charge, and this thickness, suppose this is your like conductor, okay? So this is the gray region. What
So
will
in
be the
hollow region field and out of the bulk region field, both are I think opposite to each other. Is it right, ma'am? I
okay?
guess.
So you're saying there'll be a field here, right?
Inside field in one direction and out of the bulk opposite to that inside field direction.
Okay, so regarding directions, that's that's something that will come to it. But
Oh,
first is, so you have a charge inside. So you are saying there'll be some field here,
yes,
right?
hollow in
In the
hollow
center.
region field is there.
Yes. In the thickness, there is no field. Here
Yes,
in the gray region, there is no field. And then there'll be some field here.
yes.
Yes. Okay. So this is absolutely correct. And why is it correct is because if you look at it intuitively also, you'll see that you have some charge here. So there'll be some flux lines in this region, right? So if you consider, even from the Gauss's law, if you consider a Gaussian surface here, any surface, okay, of any shape, it will enclose some charge, right? It will enclose this charge Q. And because of which you'll have a net field. Okay. So this tells us that the field inside will have the effect of this charge Q, and therefore it will be non-zero, right? How the field will be? So what you have to do? So if you have to calculate the field, how do you do it? So you have to use Gauss's law, right? So you can consider a So anywhere here or anywhere here, in whatever region, location from the charge, based on this distance from the charge, like what is this distance, right? You have to consider a small Gaussian sphere. If it is in this location, you have to consider a sphere accordingly. Like consider a small region, okay? And then you have to use Gauss's law, which tells us that the force should be given as, if this is Q, the charge enclosed is Q, and the distance between the charge and your, surface is like here, if it is R, then it's given as Q by 4 pi epsilon naught R square, right? So that is our Gauss's law. And it will be radially outward because it's a positive charge. So you will have a radially outward field lines going from here, right? You will have field lines just ignore those spikes. Basically, you will have field lines going like this. So based on which direction you are, radially from the charge, you will have a net field. Okay. But what happens in this region is, this is the bulk of your conductor. And the bulk of the conductor, there is no charge, no field. That's what we discussed, right? Now, how to understand this in terms of Gauss's law? See, if you like just by looking at it, now if you consider a Gaussian surface like this, it will still enclose this charge, right? So does that mean that Gauss's law is not valid here? No, right? There has to be something. So what are we missing here? So suppose if you have some charge here, there's this hollow region, we know that the field inside is non-zero, fine. But this is the bulk of the conductor. And we know that the bulk of the conductor, the field goes to zero, right? But if we use Gauss's law, just by on the face of it, if we just consider a Gaussian surface, there is a net charge Q, right? So does that mean then that the field here is non-zero? Is Gauss's law, or if Gauss's law is then not valid? What do you think is the, so where is the discrepancy coming from? There's no discrepancy actually, but so what are we missing basically? Any idea?
What's the question, ma'am? Pardon me.
So the question is that, see, if we just look at it, okay, and if we just want to find, one second, if we want to find the field somewhere in the bulk of the conductor. Now, in this hollow, like in this hole inside the conductor, there is a net charge, right? So now if we consider a Gaussian surface like this, okay, which encloses this charge. So according to our normal Gauss's law understanding, there is a net charge Q, right? So why is the field inside the bulk of the conductor going to zero? Or is Gauss's law not valid here? Like what is the thing that we are missing?
Okay, inside that red closed surface, field should exist, madam. Because
But-
halo region is there.
But as you just said, that this is the bulk of your conductor, right?
But it is
So,
enclosing that halo also, no?
Yeah, it's enclosing a hollow. Basically considered suppose consider a metal sphere, and inside that metal sphere there is a hole, and in that hole you have put a Q charge.
Okay.
Right? Now in that hole there'll be a net field because of that Q charge. But the annular region, the thick region of the metal,
Yes.
there should we expect to have a field, or should we don't expect to have a field? That is this region.
Yes. Got understood the question, but
So what do you think the field here should be?
actually into the halo, the field should be normal to the surface as per my knowledge. So into the halo, it is inside direction. Out of the that bulk, it is external direction normally leaving.
That is fine. So you are talking about this region, this surface. If
Yes.
you talk about this surface, that is okay. If you talk about the other surface, that is also fine. What happens here inside?
Yeah, that I don't have idea.
So based on our discussion till now, about conductors, we just told that in the bulk of the conductor, the field should go to 0, right?
Yes.
So,
Yes.
so according to our current discussion, the field in this bulk of the conductor should be 0, while the field in this hollow region should be present because of the Q charge. So this should be a non-zero quantity, right? Here it should be a non-zero quantity, but here it should go to 0, right? Inside the bulk. That is our understanding till now,
Yes. Yes.
according to the discussion that we had.
Yes.
But the problem is that if this is true, which is actually true, which is like we just discussed, so that is true. But then if we now consider a Gaussian surface like this, right? Just consider a Gaussian surface which encloses a part of your bulk of the conductor and also the hollow region. So then what happens? You do have a Q charge here, right? So does that mean that the Gaussian's law is not valid here? Like, or how do we explain? So see, if the field has to be 0 here, that means when we consider this surface, the net enclosed charge inside should go to 0, right? But by looking at it, we see a Q charge here. So there has to be some minus Q somewhere, right? So that the net charge enclosed by this surface, like this thing, goes to 0. So where is that minus Q? That's the question. The question is clear?
Yeah, clear, madam. Minus Q means like the charges are, it is a flow of current, right, madam?
Flow of current. So basically, there's no current here as of now, as like now.
That
We're not
charge,
talking about
charge distribution is there means there must be current in that
that will be
region.
a very instantaneous effect. So you have a field, there'll be an immediate instantaneous redistribution. It's not a, you can say, steady current that we are talking about. Okay, the very effect, like when you have this Q charge, the fact that there is a redistribution inside the conductor happens instantaneously. Okay, so
Okay.
yeah, so there's no, it's not like you will have a steady current of electrons going from this end to this end. That will not, like, you'll not be able to measure it. It's instantaneous. Okay, but my point is that consider a region like this. Okay, consider this region. This is your Gaussian surface. You have a Q in this hollow region, but we know that the field here should be 0 because it's the bulk of the conductor. So as per Gauss's law, if the field here is 0, the net charge that this encloses should go to 0, right? So now if you have a Q charge here, somewhere there should be a minus Q to balance it, right? Now, based on our discussion so far, that there'll be redistribution of charges, there'll be induced polarization in the conductor. Can you tell me where this minus Q will get originated? Like, where will it be?
Maybe on the surface of inside that halo.
Yes, exactly. So basically, because of this plus Q charge, what will happen in the bulk? There'll be a redistribution. How will that redistribution be? So the electric field lines here are basically expected to go like this, right?
Yes.
So because the electric fields are in this direction, what will be the direction of flow of electrons? The electrons will flow inward because they are
Yes.
negatively charged. So because of which, just ignore the spikes, but because of this, what will happen is there'll be an effective negative charge induced in the inner surface of your conductor. Okay. Now, because there'll be an effective negative charge induced here, there has to be an equal positive charge some around the outer surface. Because why? Because the net conductor is effectively neutral, right? So there is a redistribution. So then you have a positive charge all throughout your outer surface, right? So the net induced charge on the inner surface is minus Q. Okay. And here you have a plus Q induced on the outer surface. So now if you use your Gauss's law, so if you consider a Gaussian surface like this, what will happen? The net charge enclosed is always 0, right? Once you take into account this surface, which has a minus Q, Q plus minus Q, so basically this goes to 0. So you have 0 enclosed charge, and the field inside the bulk of the conductor goes to 0. So all that we have been discussing, Gauss's law and the properties of conductor, all of it are consistent, right? Now, what happens outside in this region? If we now consider a Gaussian surface here, what will the field be?
It is
Consider,
exponentially decreasing, I think, exponentially decaying as the distance increases from the outer surface.
why do you say exponentially decreasing? Like, why is this exponential factor coming in here? Or
Uh,
like, what's the origin you think?
a field is inversely proportional to the distance from the surface.
Field goes as 1 by r square, right?
Yes, yes.
Yes, there's no exponential factor here.
Yeah,
Exponential
inversely
is e to
proportional
the
to square
power.
of the distance. Yes.
Yeah, there's no exponential factor. Okay, it's proportional to 1 by r square. Here, so that means if you have something like some point at a distance r, you will have a field which will be given as 1 by 4 pi epsilon 0 q by r square. That's what you're saying, right?
Yes, the field
So
is maximum on the surface, and as we move away from the surface, the field gradually decreases as the inversely
okay,
proportional to the square.
okay, okay. So that means there'll be a field here, there'll be a field here, but
Yes,
there'll be no field here,
yes,
right? And even here, the Gauss's law will be valid. So you will have a 1 by r square dependence. And again, here you will also have a 1 by r square dependence. Very good. So this point, like now, if you think about it physically, this is very interesting, right? So you have a region where there is no field. So imagine field lines, okay? You have field lines, you have flux here, non-zero flux. So field lines here. You again have field lines here. But in this region, there is no effective field line, okay? Very interesting, right? There's a discontinuity that is now happening. So what is happening is that even though there is a region of zero electric field, this information of the charge that is inside the hole gets transmitted to the outer world, right? So suppose if you measure the field here, you'll be able to tell that somewhere inside you do have some charge Q, right? So suppose at some r distance you measure the field and you get a field. So you say that if this is the field, that means there has to be this much amount of charge inside. So the information of the charge that is inside this hollow region transmits to the outer world, even though there is this region of zero electric field surrounding the charge. Okay. And so thinking about it is quite interesting, right? Now, if you have some charge Q here, any Q charge here, will that affect the field that you have inside here? Will that change the field that you have here?
like force will exert between those 2 point charges based on the magnitudes of the charges.
But why do you say so? See, if there is
According to
a field,
Coulomb's
there
law,
is a force. So
no,
there,
no, both 2 charges are existing, madam. According to Coulomb's law, some
so
force
yeah,
may.
okay. So what is Coulomb's law? Coulomb's law, according to Coulomb's law, if there is an electric field E, then the force experienced is Q into E, right?
Yes,
So if you are in free space, and you have a charge Q and then you have another charge Q, they'll exert force on each other, right?
yes,
Why? Because this charge will create an electric field. Similarly, this capital Q charge will also create an electric field, and that electric field will exert a force on this charge. Good,
okay.
very good. So for Coulomb law, according to Coulomb's law, for a non-zero field, there has to be a non-zero force, there has to be a non-zero electric field. And for an effect, okay, so basically, if this Q charge has to exert a force on capital Q, the field around this point, right, needs to be modified by the presence of this capital Q charge. Do you agree?
Yes, ma'am, I agree.
Yes. So the field due to the capital Q should change the field here. Only then this capital Q can exert a force on the small q charge. Right? Now use your Gauss's law. Right? We just discussed that in Gauss's law, it just depends on what is the charge enclosed. Right? So if you consider a Gaussian surface inside your cavity, the charge enclosed is Q. Anything outside, will that affect the field that you have here?
It may affect, madam.
How will it affect?
Maybe repulsion type.
So just think of the fact that suppose you have, how do I explain? So basically you have a capital Q suppose charge here. Okay.
Yes.
Now for this charge to have, now you want to find what is the field at this point. Okay. Now what will you do? Based on like our typical Gauss's law, if we have to do it mathematically first, what will we do? We'll consider
R square.
Q
by 4 pi r square.
Small q by 4 pi r square. That's our electric field at this point, right?
Yes.
Is the capital Q changing the electric field at this point?
Electric field due to small charge?
No. No. There is an electric field at this point due to the small charge. That is small q by 4 pi r square, right? Now, there's also a field because of the capital Q, right? Outside, all throughout this region. Now,
yes.
If this capital Q, is this changing the field at this point?
It will change. It will get affected.
Okay. So, let me rephrase. So we know that when we have to find a force, a field at a point, what do? We consider a surface, okay, and we see what is the charge enclosed by that surface, right? So here, if we have a small Gaussian surface at a distance r from the small q charge, we know that the charge enclosed is small q, right? Any charge that we have outside, whatever be it, that is not enclosed inside this region, right?
Okay.
You agree, right? This charge is not enclosed in this surface, in this region.
Yeah, out of that surface. This charge is out of that surface, first surface.
Exactly. So that tells us that the field at this point should be affected by Q, the small q, okay? If we think about it in terms of, now suppose let us think about it in terms of flux, okay? This was mathematical, right? Mathematically, we understood that from Gauss's law, at this point, only be affected by the small q charge. It should not be affected by any capital Q, any charge that is outside in this region. Okay, that is mathematical. Okay. Now let us think about it in terms of flux. Okay. Now, at this point, we'll have flux lines going like this, radially outward from the positive charge, from this plus q charge, right? Like this. So there'll be a net flux at this point because of the small q charge, right?
Yes.
What will happen for the capital Q? The amount of flux that will go in will also go out, right?
Yes.
Basically, this flux lines is not going to get affected at the point here. So the flux is not reaching this point, and that's the reason why according to Gauss's law, this is not affected by any capital charge or any charge that is outside. So what this is telling us is that basically the field inside this field is not affected by any charge that you have here. While the field outside, so if you want to find the field outside, that is affected by the charge that you have inside. So anything that you have inside is caged from the field lines that you have here. Okay. But the outside world will have a net field because of the charge inside. Clear?
Yes, clear, but okay. Some was 50-50.
Okay, 50-50. Okay. Like if like,
ma'am, can you explain that graphically from small q, if I take a distance r from small q onwards, as the distance increases, how the magnitude of that field varies?
It will go as 1 by r square. Typical your.
No. in between there is a like discontinuity is there, na madam? In between discontinuity is there for that
No,
bulk
so here
region.
it will go to 0. That's the thing. So here at this point inside this region, there'll be no field.
Also, that field exists two different fields, I think, from 0
Yes,
to
yes.
R, 0 to
So
R1. Uh,
yes. So here, suppose this region. So let us like do a simplified thing. So suppose something like this, where the radius is okay, very bad. Uh, 1 second. So basically, if your radius was well defined, okay, consider this one as A and this one as B. So then what
hmm.
will happen is you will have a field which will be decreasing and it will go to A 1 by 4 pi epsilon 0 A square, Q by 4 pi epsilon A square. It will have that and then it will go to 0 in
Okay.
this region. And again, here you will have the, it will start from B and then go forward. Like B to R, as you increase your radial distance, it will go as 1 by R square. Okay. Like if we, there'll be similar kinds of questions in the coming slides. So I think then it might clear your confusion.
Okay.
Okay. Just hold on. If you have doubts, still doubts are there, you can ask. Okay.
Okay. Thank you.
So this is what we have discussed so far. So the field here is non-zero. The field out in this region will also be non-zero, but inside the field will go to 0. Now, based on all the discussion that we have, now if you want to answer this question, an uncharged spherical conductor centered at the origin has a cavity of some weird shape. Somewhere within the cavity, there is a charge Q. What is the field outside the sphere? Right? So, as like whatever discussion we have had till now, we now know. So there'll be a Q charge here. So there'll be a induced minus Q on this surface, the internal inside surface, and then there'll be a plus Q on the outer surface. So if we take a Gaussian surface somewhere like at distance P, now if you take a Gaussian surface, the net charge enclosed will be Q. Q plus minus Q plus Q, effectively Q, right? So that means you can just do this, right? Using your Gauss's law, it will anyways turn out. The Q is the charge enclosed, so 1 by 4 pi epsilon 0, Q by R square, where R is the distance from this point. Here, this is what we had been discussing so far.
Yes, ma'am.
Okay. Now let us try to answer this question. Okay, so this I think will make things clearer. So here, you have two spherical cavities of different radius A and B, and then you have a bigger, conducting sphere of radius capital R, inside which these two cavities are, and at the center of each cavity there is a point charge QA and QB. Now let us try to solve each of this question part by part. Okay, so what is the surface charge sigma A, sigma B, and sigma R? That means, what is it telling? So because of this plus Q, like QA or QB charge, there'll be an induced charge on this surface, right? That's what we discussed. Now, if we want to find the surface charge, sigma A, what does it mean? It's the charge per unit area, right? On the inner surface. Similarly, sigma B will be the charge on this inner surface. So by the area, charge per unit area. And similarly, sigma R will be what is the charge on the outer surface per unit area. So based on all our discussions so far, what do you think sigma A, sigma B, and sigma R should be? So the radius is A. So the surface area, if we say, it will be 4 pi S square, right? What is the charge induced on the inner surface? The total charge induced?
Sigma A into that surface area.
No, wait. Sigma A is the charge per unit area. Okay. Total charge
Charge
by
density. Surface charge
charge
density.
density. Charge density, exactly. So for that, what we have to find? We have to find the net charge, the total charge that is induced, and divided by the area, right? Now, the radius is A, so the area is 4 pi A square. What is the
Yes.
charge that is induced on the surface? The net total charge. What will that charge be?
Sigma A into sigma A by 4 pi A square.
You mean Q, right? Sigma A
Yes.
is equal to
Q into 4 pi A square.
Q by,
Yes,
right?
yes, ma'am.
Divide.
Q
Yes.
Q by 4 pi A square.
But there is a small mistake. What we are doing is that the charge induced here will be negative, right? Like opposite of QA. If this
Oh,
is positive charge, here you will have a negative charge, right?
okay.
So basically the charge induced will be minus QA, and so the surface charge density will be minus QA by 4 pi A square. Clear? Similarly, here it will be minus QB by 4 pi B square. Clear?
Okay.
What will be sigma R? So sigma R will be, so you have two charges now, QA and QB. So here all throughout, so if we just do it like this, so you'll have a negative charge all around, which is minus QA. Again, you will have negative of minus QB. But here you will have positive, right? Again, you will have positive charges here. And this positive charge will have effects of both QA and QB. So what will be the total charge on this outer surface?
QA plus QB by 4 pi A plus B whole square.
Not A plus B whole square, 4 pi R square, right? Because
Yes,
your
I get.
area is R, like this
Yes.
radius is R, so 4 pi R square. So that means
Yes.
the charge will be given as like this. Clear?
Oh,
Now, what is the field outside the conductor? Okay, so what is the field in this region? So again, what is the net charge that is enclosed? The net charge, so here you have QB, here you will have minus QB induced, QA minus QA induced, and on the surface you have QA and QB. So now if you take a Gaussian surface, the net enclosed charge will be QA plus QB, right?
right.
So what is the field outside the conductor? It will be given by this relation.
Yes, correct.
Where is my pointer gone? Okay. So this is the relation, right? Now, what is the field within each cavity? Okay. There's someone waiting in the lobby. Okay. So now, what is the field within each cavity? So what is the field here? Again, we'll take a small Gaussian surface. So the net charge enclosed will be QA. So anywhere inside, you'll have a field which is given as QA by 4 pi this distance square, right? Similarly, here, somewhere here, you will have QB by here. So something like this. So RA, RB is the vector from the center of the cavity to the point where you want to find your field, right? Now, what is the force on QA and QB? So what do you think the force on QA and QB should be? So there are two charges in two cavities. Now, for this to experience a force, there has to be a net field because of this QB charge, right? Similarly for the other one. So now if we look at this charge, will this QB charge affect the field that you have here? No, right? Because this is in a different cavity. So this is actually not enclosed. So whatever charge, if you want to find the field somewhere inside this cavity, it will only enclose QA, right? So the field here is not affected by any charge in any other cavity anywhere. Okay. So that means there should not be any force because of this charge on this and vice versa. Clear? So the force on QA and QB should go to 0. because these are isolated systems. So this charge is isolated from this charge. Okay, and like this region has no field. Now, what happens if we bring a third charge, QC, near the conductor? How will this, what all parameters you think will change? You have brought a QC charge somewhere near. Will the sigma A, sigma B, sigma R change? Will E out change? Will EA, EB change? Or the forces change? What will change and what will not change? What do you think? See, sigma A, sigma B should not get affected, right? Because this just depends on what is the charge induced here. What is the charge induced here? And that is not affected by what you have outside. So sigma A, sigma B will not be affected, but sigma R will be, right? Because sigma R is in presence of, like, is exposed to this QC surface charge. So QC will affect sigma R, but not sigma A, sigma B. As we had discussed, the force will still be zero. Force on this, there will be no force on QA or QB because of QC. So the force will still be zero. Will E out change? Definitely, right? Because now you have an extra charge. So somewhere here, if you want to find the field, obviously that field will be affected by this charge. So electric field outside the conductor will get affected by a third charge. Okay. But what happens to the field inside the cavities? There, anything outside does not affect the field inside, right? Because this charge is not enclosed in any surface area that you consider here. Clear? So what it is telling you is that sigma R changes, not sigma A and sigma B. E outside will change, but not EA or EB, and the forces will still be zero. So that means whatever you have inside this conductor, so if you have a metal conductor and if there is a hole inside and you put some charge there, that charge will actually be isolated from all the charges that you have outside. But the outside field will be affected by the charge that you put in the cavity. Okay. So it's a sort of caging. Now, similar thing can also be, so the same idea can be used to answer questions like this. So here you have a metal sphere of radius r carrying charge q surrounded by a thick concentric metal shell. The shell carries no net charge. Okay. So here there is this is a metal surface which has a charge q. Okay. And this concentric ring has no charge. Now, what is the surface charge density sigma at R, which is like on this surface, at A, which is the inner surface of the shell, and B, which is the outer surface of the shell. So for this, you have to consider how the charges get distributed, right? Again, similar thing. So here you have charge Q. It already says that your metal sphere has a net charge Q, and the radius is R. So what should be the surface area, the charge density at R? It should be nothing but Q by 4 pi R square, right? Total charge by area. So that is your sigma R. Okay. Now what will be at A? There will be again a negative charge that is induced, right? So if I write it like this, it will be a negative charge, and then you will have a 4 pi A square, because this surface has a surface area which is given by radius A, right? And what will happen to this? Again, it will be a positive charge and divided by the area given as 4 pi B square. Clear? So this is how you look at charge densities. So when you talk about charge densities, be careful about this signs. Okay. This is what is important to remember. So when the nearer surface has a negative opposite sign, well, this one has a same sign. So that's important to remember. Now, find the potential at the center. Okay. So what is the potential at the center? To answer this question, we have to go to the definition of potential. What is potential? Potential is work done to bring a charge from infinity somewhere very far to this point, right? So basically, if we know the electric field and if we do a line integral E dot dl from this infinity point to the center, that should give us the potential, right? So that means if we want to find the potential, we need the information of the electric field, right? Now, we need the electric field in this region. We need the electric field in all the regions, like all along this region. And then we have to do a line integral. So basically, from infinity, minus of infinity to 0. 0 is your center. Now, what will be the field from infinity to point B? That will be given as 1 by 4 pi epsilon 0 q by r square, because the effective charge enclosed is q, right? Anywhere in this outside region. What will be the field in this region? Like the thickness of your shell, it should go to 0 because it's a conductor, a metal piece. So the field from B to A will be 0. What will be the field here? Again, you have a charge, right? And that charge is again given by the charge that you have on the sphere. So you have q by 4 pi epsilon naught r square. Okay. And that goes from A to R, like this central, this white region. Okay. Like this region. And then inside this part, it will again go to 0 because it's a metal sphere. So again, you have 0. So if you look at the electric field in all these sections, as you go from, somewhere far to the center, right? So if you go on looking at how the electric field changes along this line and do a line integral, that will give you the potential. Okay. So that gives you the value of potential at the center. Now the outer surface is touched to the grounding wire. So that means what the question is telling is, whatever charge you initially had, it's being grounded. So sigma B should go to 0, right? So if sigma B goes to 0, what happens? That's the question. So if the outer surface is touched to the grounding wire, which lowers its potential to 0, how does the answer change? So according to our, what do we consider? We consider the potential at infinity to be 0. Now, because this part is grounded, okay, so that means sigma B has gone to 0. So effectively what happens is the potential at this point also becomes 0. So that means there is no work done in bringing the charge from infinity to this point. So basically you will not have this term. This term basically is 0 because there is no work done in bringing it from infinity to point B because they are the same, right? So only this term, the contribution from this term would go away, right? So basically this sigma B will go to 0 because whatever charge you have on the surface will go to the ground. It's grounded. So then the other terms remain the same. So now if you do this integration, this is what you end up getting. Is this question clear? Clear, right? I'm not able to hear. I am seeing you unmuted, but uh, I don't know why your voice has been reduced so much. Yeah. Are you telling something? I'm sorry, I'm not able to hear. You can also write on the chat box if needed. Any doubt, please write. Okay. I'm not able to, I don't know why your voice has reduced so much. Not able to hear. If you have a doubt, just write it in the chat. Okay, clear. Okay, good. So this was about conductors and induced charges. Okay. Now, based on our understanding so far, we have discussed about the relations between electric field and how electric field is related to potential, what is the relation between electric field and charge density. We also talked about what happens inside a conductor. So that's our current state. Okay. Now, with all this information, let us do a practical kind of problem. Okay. This is like an application of what we have been talking so far. So if we want to find what is a PN junction, okay, so here in a PN junction, basically you have a region where you have more electrons and this has more holes. So now in this PN junction, there is this region which is called the depletion region, where basically the electrons move from the N side to the P side, and this has some charges, right? So there is a positive charge near your N side and there is a negative charge density near your P side. Now, so what is this? Basically, it has some charge density. Now, if we want to find the field and potential because of a PN junction, so we can again use whatever we had been talking so far, right? So what is this telling us? That for this PN junction, you can say that now this depletion region, okay, so whatever region you have here, there is this positive part, there's a negative part which is close to the P because electrons flow from N to P, okay, and anywhere here it's neutral, right? So you, based on the charge, like the donor and the acceptor concentrations, you can have a region, a length till which you have your non-zero charge density. Okay. So in the N side, this distance is said as x n0. In the P side, it is given as minus x p0. Okay. So this is your length, the region where you have a non-zero charge density. So now if you say that, so here if you say that the donor concentration is ND, and then you consider some area A, and you have a length given as x n naught, and the charge for each donor is given as Q, then you can basically find the net positive charge in this region, right? Which is given as QA x n naught into ND. ND is your concentration of donors. Similarly, here you can find Q minus, which is minus Q A x P naught into Na, where Na is your acceptor concentration. So this is the net charge that you have in this region, and the net charge is, that you have in the positive region. So what is the charge density? Basically, you divide by A x naught. That's your charge density, right? So in the positive, in the N side, basically, here you have a charge density given as Q into ND plus, and on the P side here, you have a charge density given as minus Q Na minus, right? So these are the charge densities that are given. So now that you know the charge density, basically what you know is rho, right? So if we now go back to what we have discussed previously, we know rho. What do we want to find? We want to find E. So can you tell me what is the relation between rho and E? What is the relation between rho and E? If you know rho, how to find E? We know sigma. Okay, so this image is in, like, it looks like 2D, but basically it has an area into the length. So consider it as a 3D object with some volume. So then you have volume charge density, right? So here this term A is the area, and then you have this dimension, which is the, you can say, the length. So A into x n naught will be the volume of this positive region. Similarly, A into x p naught will be the volume of this negative region. Okay, so you're talking about volumes. So that means you know rho. Okay, so once you know rho, that is the volume charge density, how do we find electric field? What is the relation that we should be using? Any idea? This is something from the last class, right? We had talked about all the different kinds of relations between the charge density and electric field and potential, right? Which also comes from Gauss's law. So there is this relation that divergence of E is equal to rho by epsilon naught, right? So that means if you know rho, you basically know divergence of E. What is divergence of E? So if you have a field E given as Ex I cap plus Ey j cap plus Ez k cap. So what is divergence of E? That is del Ex, del x of Ex plus del y of Ey plus del z of Ez. So here if we talk about one dimension, divergence of E is nothing but del E del x, right? So basically you know del E del x. you have to find E. What you have to do? Integrate. Clear? Understood? You know rho, that means you know del E del X. You have to find E. So what you have to do? Integrate. Okay. Now, when you integrate, there are certain boundary conditions that you have to remember. So what are the boundary conditions? First is that in this region, basically in this regions, the edges of your depletion region, there beyond this, it's a neutral region. So the field should go to 0 in this region. So field at minus x p naught should be 0. Field at x n naught should be 0. Okay, so that's a boundary condition. Another condition is what? Because you have this positive charge here, negative charge here, so there's a crossover of flux, basically flux moving from one side to another. So that tells us that there has to be a maxima at this junction 0. Okay, there has to be a maxima at the x equal to 0 point. So these are our boundary conditions. Now let us apply basically this relation. So we know del E del X. Okay, so for 0 to n naught, which is this region, the one at the n side, that is given as, what is the charge density? QND plus, right? So that means del E del X should be QND by epsilon. Now on the other side, which is the P side, that is from minus x p naught to 0, there again you have del E del X. Now the charge density becomes minus QNA by epsilon. Clear? So if you have this, now you have to do an integration. That's what you do here. So you do an integration from 0 to x n naught for the n side, and from minus x p naught to 0 for the p side. Okay. So if you do that, what do you get? This is your electric field expression. So at the center, at x equal to 0, you have a maximum value, but that value is negative. Okay. And this is also understandable from the fact that you have a positive charge here, you have a negatively charged region here. So the field should move in the minus x direction. Okay. So that tells us that your field should be negative here. So this is what you get. You get a negative field. You have different slopes. Why? Because your charge densities are different. In one, you have QND plus. In other, you have QNA minus. So based on this charge densities, you have different slopes, and you have a maximum value at x equal to 0. So this is how your field will look like for a PN junction. Okay. So this is the value of the maximum field. Now, once you know the field, you can also try to find the potential. Because what's the relation between electric field and potential? We know that E is equal to minus grad V, right? So equal to minus del V del X. So again, you can do an integration to find potential. So now what is integration? Integration is nothing but the area under this curve, right? When you do an integration of E as a like E dot dx, you're basically finding the area under this curve. So that means it would depend on half into the height and the width. This width is called W, which is your width of your depletion region where you have this charge. Anywhere outside, it's neutral. Okay. So that means now you can relate your potential, which is called the contact potential, to the width of your depletion region by this relation. Okay. So again, if you now know the depletion region, like the width, you can also find the potential like this relation. Okay. So that is telling you how the potential in a PN junction depends on, what does it depend on? It depends on the width. It depends on Na, Nd, which are the charge densities. Okay, the concentrations of donor and acceptor concentrations. That's what it depends on. Okay, so you can again rewrite it further in terms of basically rewriting this term. So if you know the potential, if you know the carrier concentrations like the charges and of the donors and the receptors and the medium, so you can actually find the depletion width. depletion width is the length, this region of the depletion region. Okay, the length of the depletion region. So that's again dependent on this doping concentrations. Okay, and that's how you write it. So now, considering that W is nothing but xp naught plus xn naught, you can basically write what is the penetration in the x side, what is the penetration in the y side. So that's how you can write xp naught and xn naught in terms of the doping concentrations and the carrier, the contact potential. Okay, that is V naught. So there can be questions directly based on this derivation. Okay, while there can be questions where the values are given, you have to find what is the depletion width or things like that. Okay, but basically this is simply using our well-known relations of how rho is related to electric field, how electric field is related to potential, and doing normal integrations. Okay, is it clear? Any doubt here? Any doubt in this region?
No, ma'am. Clear, clear.
Yeah. Okay, thanks. Okay, so now let's move on to this idea of capacitance. Okay, so what is capacitance? Is basically, so if you have a like some, okay, what do I say, some material, okay, and you apply some charge to it, and that tells that it is in some certain potential. Now, how much charge has to be added so that there is a unit potential rise? This proportionality constant is what is capacitance, basically. So if you know the charge and you know how much is the potential because of that charge, you can find the capacitance of any nature. So before going about capacitance, let us closely look at this, boundary conditions. So here it tells us that if you have some region, okay, some surface with some sigma charge, and there you want to find what is the relation between the perpendicular component of electric field above and below. So what you can do is you can consider this Gaussian pillbox of some thickness epsilon and area A, and then use the Gauss's law, which is nothing but this. So you're doing the integral form. So here, what this tells us is that, so E dot dA, so basically you will have this surface at a, like, so if the sigma is the charge density, the net charge enclosed is sigma into A. So sigma into A by epsilon naught should be given as this surface integral. And this surface integral again can be written as E above into A minus E below into A. So that gives us a relation like this, which tells us that there is a difference between the perpendicular component of electric field above and below. Okay. While if you look at the tangential or the parallel component, so for this, now if you consider this small, line integral, like this curve, like, what do I say? This closed curve, okay, like this, of some length L and a very small width epsilon. So as epsilon goes to 0, that means you're looking at the surface above and below, just immediately above and below, and you want to look at the tangential or the parallel component. So there, what happens? As epsilon goes to 0, there is no net epsilon like charge enclosed. So that results in the fact that the parallel components are continuous. So that means if you have a surface with a net charge sigma, then there'll be a discontinuity in the perpendicular component, and that will be given as sigma by epsilon naught. So you can write the electric field as sigma by epsilon naught n cap, where n cap is the direction of the normal. Okay. Once you know the relation between sigma and electric field, you can also write a relation between sigma and potential, because electric field is nothing but grad minus of grad V. Right? So this relates the potential difference with the charge that you have, the charge density that you have. Okay. Now consider two infinite parallel planes which carry equal but opposite uniform charge densities, sigma and minus sigma. Okay. Now we want to find the fields in the three regions. One is at the left of both, one is in between, and one is to the right. So what do we do? Basically, now again you can consider Gaussian field boxes like this to find what is the field, right? So the left plate, if you just look at this plate, okay, so it will produce a field which is given as sigma by 2 epsilon naught. Now because it's a positive charge, the field lines will go outward from the charge, right? While for this minus plate, the field lines will go inward into the plate. Okay. So that means what will happen is for this plus sigma, you will have field lines like this, okay, going outward from the plane. For the minus sigma, you have field lines going into. So for this kind of field distribution, what happens is that anywhere to the left or right, the field cancels each other, while you get a net field from the plus to the minus direction inside these two parallel planes. Now, why it is important is that means if you have two parallel infinite planes, there is no field in these two regions. Only inside you have a non-zero field. Now, because you have a non-zero field, that means you have a potential difference between the two. Okay. So now once you have a potential difference between the two, okay, you can define a capacitance for it. Now, this idea of capacitance also comes from the amount of work done, basically. So because you have to have this potential difference, you have to have a charge difference plus and minus between the two. So that results in a net work done that has to be done for this charge to be distribution to be there. And that comes from capacitance. So if we want to find the capacitance for this parallel plate capacitor, which is considered two metal surfaces of area A and distance d apart, so we know that the field inside is given as 1 by 2 epsilon naught into sigma plus 1 by 2 epsilon naught into sigma because they add up. So basically sigma by epsilon naught, that is the field inside these two plates. Okay. So now what is the potential? Because it's a constant quantity, we can just directly multiply by the distance, right? So basically you have this value. So sigma is nothing but capital Q by area, right? That is the charge density by epsilon naught, which is your field, into d, which is this distance. That is your potential difference between the two plates. And now you know what is the charge, right? Because you know sigma. So you know Q is nothing but, sigma into A. So if you want to find capacitance, what do? You find the potential difference. You know what your capital Q is. So basically use this relation Q by V. So if you do that, that gives you the value of the capacitance, which tells us that how much charge has to be added to cause a unit potential difference between the two. Okay. So this is your value of your capacitance. Here. Now, what does it depend on?
Only on the physical dimensions of
your metal surface. It depends. Yes.
Physical dimensions of that material, surface, metals.
Yes. So it depends on the dimensions. It also depends on the inside, right? Because here you have epsilon naught because it's air. If you have some other material, obviously that the material property will also come in, the medium properties. So if you go back to our basic understanding of, how the electric displacement came in, we had discussed briefly that in the last class where you had a polarization, and because of the polarization, there was this electric displacement. Basically, the definition of electric, dielectric constant. So if you have a different medium with a different dielectric constant, that will affect the field that you have inside, right? So the field will get affected, so the potential will change. So basically, your epsilon naught will then be replaced by epsilon, which is the permittivity of your medium that is there. Okay, so it depends on the medium, it depends on the dimensions of your metal surfaces. Okay, so now find the capacitance of two concentric spherical metal shells of different two radius A and B. Okay, so again, what do you have to do? We want to find the capacitance. So for that, we need to find the potential difference between these two surfaces. Right? We have two metal shells. We want to find the potential difference between the two. For that, we need to find the field between the two, because if we know the field, we can find the potential. Once we know the potential and we know the charge that is there, we can find the capacitance. Okay. So for this, we want to find the field between the spheres. Okay. So for this, we know what is the field, right? We use a Gaussian, like the Gauss's law. Consider a Gaussian surface. The charge enclosed is plus Q. So E is equal to Q by 4 pi epsilon naught R square. So the potential difference between them will be E dot dl from B to A. Okay. B is the outer radius, A is the inner radius. What is the work done to bring a charge from this point to this point? So this is the relation. So this is your potential difference between them. So what is capacitance? That is nothing but Q by B, which is this. Okay, so this is your expression for capacitance. So whenever you have to find the capacitance, you have to look for ways to find the potential. For that, you have to either directly find potential. In many cases, that might be easier. Laplace or like Laplace equation can be used, or you have to find electric field and then find potential from there and then find capacitance. Okay. Now, to charge up a capacitor, what you are basically doing. So what I said is, what is the definition or idea of capacitance is basically how much charge you have to add to increase the potential by a unity, right? That is your capacitance. So what do you mean by, adding charge? Basically, you have this two surface. One is plus Q, one is minus Q. So basically, you have to increase this negative charge, and you have to also increase the magnitude of basically you have to increase the magnitudes here, right? So that means you have this negative surface, you have to take some electrons out of this, basically you have to put in more charges here, right? So more electrons has to be added to it, and more electrons have to be taken away from the positive charge, so that the net positive charge increases and the net negative charge increases. But that's difficult, right? Because this is already a negative charge. So adding more electron to this negative charge needs work to be done. So to charge up a capacitor, you have to remove electrons from the positive plate and carry them to the negative plate. So for that, you have to do work against the electric field, right? The electric field is directed in this direction. So you have to do work against it, which is pulling them back towards the positive conductor and pushing them away from the negative one. So how is this work coming from, right? You have to do some work. So that work is actually you can say the is a measure of, again, the potential energy that is stored in the capacitor. Okay. So if you say that in an intermediate state, the charge is small q, okay, so the potential difference is given as small q by C. C is the capacitance. So what is the work done for the transport of, next piece of delta Q charge? That is nothing but potential into the charge, right? Work done is potential into charge. So potential is Q by C, potential difference, and charge is dq. That is the amount of work done to move a dq amount of charge between this potential difference. So now if you want to charge it from 0 to capital Q, you do an integration. So this gives you the total work necessary for charging your capacitor. Okay. Again, if you use the relation between charge and capacitor, replace it, you can actually write the work done in terms of the capacitance and the potential difference. Okay. So if you know the potential difference between your two metal surfaces and you know the capacitance, you know how much amount of work you have to do to charge your capacitor or charge this metal surfaces to a particular charge Q. Okay. Now, There can also be questions like this, where you have to find the capacitance per unit length of two coaxial metal cylinder tubes of radius A and B. So again, here it's the same thing. You have to find the potential difference between these two surfaces, the inner, tube and the outer tube. Okay, so for that you have to find the field. So what you do, you consider a small Gaussian cylinder, okay, and try to find the field. So again, you can consider that the charge on the inner cylinder is capital Q for a length L. So by Gauss's law, you can consider a Gaussian cylinder here, okay, in this region between the two tubes. And then E dot 2 pi SL, 2 pi SL is your curved surface area of the cylinder, right? So E dot 2 pi SL will be equal to the charge enclosed by epsilon naught. What is charge enclosed? That is again capital Q, which is given in your question, like you have considered it to be Q. So that is nothing but Q by epsilon naught. So this gives you the electric field between these two tubes. Once you know the electric field, you can find the potential difference, which is nothing but E dot dl from A to B. So this is the relation. And then basically Q by V, which is your capacitance. Okay, so here per unit length, so you can divide it by length. So that's how you find capacitance for different kinds of structures. Okay. Now, because we have been talking about capacitance and medium and induced charges, so an important point comes in is polarization. So the fact that when you have a field, there will be redistribution of charges. So that means this redistribution of charge, like in a metal, we know that redistribution results in net zero electric field inside the conductor for a conductor. But what if it's not a conductor, but some other material, like some dielectric? So there again, there will be some polarization, right? But it will not exactly cancel out the field inside, but there will be a net polarization. Now, how much will this polarization be? That is what is defined by this term, the atomic polarizability alpha. So if you have an applied electric field E, okay, and you say that in the presence of the electric field, your atom, how much does it gets polarized? So that factor is called alpha. Okay. So normally in general, alpha, can be a tensor, but to simplify it, now we can just consider it to be just having some magnitude. So P, this is your polarization. How much is it polarized? So this dipole moment is proportional to electric field. So what we consider is that in the linear regime, when we apply a field, the amount of polarization is proportional to the field that is applied. And that proportionality constant is the polarizability. Okay. So now if you have a region where you have, so this is dipole moment. Now, if you have a region where there is a polarization, so you can define a term called, dipole moment per unit volume, which is the P, the polarization that we define. So when we talk about polarization, we talk about the dipole moment induced per unit volume because of the field that we have. Okay. So it's interesting to understand that, in the last class that we discussed, that when you have a, some material, and you have some material and then there'll be some induction of charges. So when we talk about, suppose we discussed about the relation between electric field and charge density, right, rho. But this rho might not just be your free charge, the charge that you put in. It will also have contributions from the bound charges, which comes because of the polarization. Okay. So that means this induced charges can also affect the field that you have, also affect the potential that you have. So we want to find what is the field of a polarized object, or what is the field arising because of this polarization. Okay. So for now, we can, start with this. Basically, this derivation, it will come up as we proceed in the course. But what this is telling you is that if you have a small dipole moment P at a distance r square, this is how the potential looks like. So that means now if you have a region, okay, some material where there is a dipole moment per unit volume, then you can actually do a volume integral. Okay, so if the dipole moment per unit volume is capital P, you can rewrite this for that entire structure by doing the volume integral as given here. Okay. Now then these are vector algebras that are there. So these are like, it is important to know them, but I would focus mostly on what this actually tells us. So this is your potential coming because of the polarization. Okay, you have some applied field somewhere that has resulted in a polarization. You want to find what is the potential because of this polarization. That's this. Now with this mathematics, all these steps, what you end up getting is interesting. So what this tells us is that now the potential has two contributions. One is a surface integral, another is a volume integral. Okay, so that means the potential due to a polarized object can be written in terms of a surface charge density and a volume charge density, right? Now the surface charge density is given as, if P is your polarization, that is dipole moment per unit volume, then the surface charge is density is given as P dot n cap, where n cap is your normal to the surface. And then you have a volume charge, which is given as minus rho dot P, minus divergence of P. Okay, so that means now the potential of a polarized object can be written in terms of potential due to a surface charge and a volume charge. All of this sigma P and rho B, both of them are bound charges which arise because of induction in the material because of the applied field. Okay. Now, when we discussed about the electric displacement D in the last class, we had used this relation there, if you remember. So this led to the idea of electric displacement, which again only depends on the free charges. But the relation that we have used here comes from here. Why it is important is, so now based on the material that you have, this capital P will change based on the material. Okay, so that means the bound charge will change. If the bound charge changes, all this potential will change. Okay, the potential changes, that means in a medium the capacitance, if you talk about capacitance, the capacitance will change. If you talk about electric field, the electric field will change. So all of this will have effect. The medium property will have effect on all of that. Okay, so this is what we had discussed in the last class. Basically, you can now write the Gauss's law, where rho has contributions of free charge as well as bound charge, where you put in this value, and that gives you the definition of dielectric displacement, where the displacement only depends on the free charge. Okay, and this P is the polarization. So in the linear regime, you consider P to be proportional to the applied to the field that you have. So the net field that you have, the polarization is approximated to be proportional to it. And this proportionality constant, here you have this term which is called the electric susceptibility of the medium. Okay, so this electric susceptibility, okay, here as you can see, so it helps you. So if it is a known quantity, basically it relates the electric displacement, which just depends on the free charge, to the electric field, the net electric field. So the capital E here has effects of everything. It has the effect of bound charge, it has the effect of free charge, all of it. D has the effect of only the free charge. So this is the relation that you have between the two, where this term here is the permittivity of the medium, which depends on the electric susceptibility, which determines the type of polarization that you have in the material. Okay. Now, once you find epsilon, which is the permittivity of the material, you can define a quantity called epsilon R, which is the relative permittivity, which is the ratio of epsilon to epsilon naught. That is how different it is from the permittivity of free space. And that gives you the definition of dielectric constant. Okay. So it's very important to understand how the medium properties, the polarization in a medium, can affect your fields and everything. And a quantity that governs or determines this property of polarizability is inherently there in this dielectric constant. So if you know the dielectric constant, you can use this to find the susceptibility of the material. If you know the susceptibility of the material, if suppose the electric field is given, you can find the polarization. If polarization is given, you can try to find the total electric field. Okay. You can also use this relation. So suppose D is given. Okay, the free charged information is known. So basically you know D, but you don't know what is the total effective field. If you know epsilon, which is the permittivity of the material, you can use this relation to find the effective field. Okay, so there can be all these kinds of numericals or relational questions based on these relations. Okay, all these relations. So now, if we just look at this question, we'll get an idea of how the field gets affected. So initially, we had already done questions like this where you have a metal sphere and you want to find what is the field somewhere outside. We know these are straightforward things from Gauss's law. But now suppose if it is surrounded by some dielectric material of permittivity epsilon. Okay. So now what is the potential at the center? What is the potential at this point? So whenever you're asked to find potential, basically you have to first think about how to find the electric field. If you find the electric field, you can do a line integral from infinity to that point to find the potential, right? So basically you have to find the electric field outside in this region and in the metal, like this sphere, and then do a line integral, right? So what you can do is basically, now this medium has some permittivity given as epsilon. What you say is you have a charge Q. This is your free charge. There is no bound charge yet, right? So this is your free charge. So you know your free charge. You can say that in this region R, anywhere R greater than A, in this region, your D, which is just dependent on the free charge, it does not depend on, the material property, or it does not depend on any bound charge, anything, right? It just depends on free charges. So starting from the free charge information, capital Q, you can actually find D, which is your electric displacement. So D is equal to Q by 4 pi R square. So this is basically again using the Gauss's law in terms of the electric displacement. Okay. So D is equal to Q by 4 pi R square, where Q is your free charge that you have put on your metal sphere. Now, inside the metal sphere, what happens? Obviously, electric field is zero. In anything inside the conductor, field is zero, polarization is zero, D is zero. Okay. So now things will change in this region and in the free space. So anywhere in the free space where R is greater than B, we have our typical expression for free space. So you have Q by 4 pi epsilon naught R square. While anywhere inside in this region, now your permittivity of the medium will come in. So your epsilon naught now gets replaced by epsilon, which is the permittivity of the medium. Okay. So basically now if you do the potential, this is what you get. These are just integrals, right? You do the line integral and this is what you end up getting. So initially, if there was no such medium like this, so initially if it was free space, you would have had epsilon naught here, right? But now what you are having is epsilon. Now this epsilon is so if I go back to the definition, this epsilon is some factor multiplied to epsilon naught, right? So basically what this is telling you now is that the potential here is decreasing, okay? So basically you get a net potential difference. So initially if your potential difference was something, now because of the presence of this, dielectric material, the amount of work that has to be done has now got reduced. Okay, because this term epsilon is basically some factor multiplied by epsilon naught. So this values will get reduced, so the effective potential will get reduced. Okay. So now if the effective potential gets reduced, what happens on the capacitance? Okay. So we know that C is equal to Q by V. So if V gets reduced, what happens to C? It gets increased. So basically, now your capacitance will get increased by a factor of the dielectric constant. So if you have two metal spheres, metal surfaces, and initially there was air in it, you have some capacitance C. Now, if you replace this material, like the air, by some medium of permittivity epsilon, some dielectric constant epsilon r, then the capacitance will increase epsilon r times. Okay. Now, like, I think this is clear as of now. Now, there can be all these different kinds of, structures that one can think about. Like we discussed about concentric spheres, we can have concentric tubes, cylindrical surfaces, you can have plane surfaces. You can also have isolated, yeah, yes. Yes, Ramesh?
Nothing, madam. Continue.
Okay, okay. So you can also have conditions like, isolated spheres. So basically, if we go back to the condition of, this concentric spheres, right? You had two concentric spheres. Now consider the case where one of the sphere, the outer sphere, goes to infinity, right? So then what you have basically is an isolated sphere. Now this can also act as a capacitor. It can also hold charge, right? So an isolated charged conducting sphere can also have capacitance, and what that capacitance will be. So if we look at the expression of concentric spheres and put B tending to infinity and A tending to some capital, like some r, some radius r, then you end up getting C as 4 pi epsilon naught r. So this is your potential of a isolated sphere. So if you talk about, suppose they can, like I saw a question in the last year's assignment where it was said, like it was a question on about Earth, and it was said that if you have Earth, and then if what is the capacitance for some, if you consider Earth, what is the capacitance of Earth, something like that. So all this, so in that case, you have to consider it to be an isolated sphere, and this is the relation that you will have for the capacitor. This can also come from the potential. So for a isolated sphere, if the charge is Q, we know what the potential is, right? Q by 4 pi epsilon naught R. So now if you do Q by V, which is your capacitance, you get the same expression back. So this is how one can try to find capacitance for different kinds of structures. And the capacitance is very much dependent on the material that you have between your surfaces. Okay. As we saw here, it can be affected by the dielectric constant. That's because the potential difference gets affected. Potential difference is nothing but work done. Work done is getting affected because the field is getting affected, okay? Because of the medium that you have. So this is how it can get affected. And there are all these different kinds of relations between, electric displacement, field, susceptibility, permittivity, dielectric constant that one can use. So I think that's it for today. If you have any question, you can ask me.
Madam, once go to the capacitance concept slide, please. Starting of the capacitance.
Yeah, 1 second.
Yeah.
Yeah.
Yes, madam. This one. Here, left side top diagram, your total field is sigma by epsilon naught, and below one is 0, right? Below the parallel field, both magnitudes are equal.
Yes.
Above and below. And top side, that below field should be downward, right, madam? Electric field below the sheet should be directed downward.
Yes. It's just a, like, this is just a, how do I say? It's how it is defined. You'll obviously have a difference between the two. Like if it is a positive surface, you'll have field directed upward here and downward, like downward here. If it is a negative
Downward.
surface,
No. Okay.
yeah.
Then only 2 gets added, and the resultant is sigma by epsilon naught will be getting. If both are in
Yes,
same direction, again will be getting 0, right?
yes,
Not like
yes,
that.
exactly. So this is what you see here, right? So here, if you have plus sigma, you have So in this direction, you have the field outward. Again, here it's outward, right?
Okay.
For the negative sigma, you have field coming in. So you have a
Okay.
field coming in, you have a field coming in. So this is the contribution from the plus sigma. So basically, always, like if you have any positive surface, positively charged surface or positive point, fields will be like field lines will be going outward from that, and negative fields will be coming in. So if you have a positive surface, suppose sigma is positive, you will have field lines going outward, up, like up here and down here. If you have a minus charge, you will have fields coming inward on the top, and again, like
Yes, yes.
outside, right?
Flux lines
Yeah,
terminate on the negative charge and originate from positive charge. That is the concept.
exactly. Yes, exactly.
That's right.
So that
And
will always be there. Yeah.
Hmm.
Tell me.
That polarization mathematically I understood very well, madam. But logically, is it whether a dielectric atom, how all the charges are strongly bonded? Is it possible to create a polarization there? Like polarization means separation of charges, right, madam? Positive and negative
Yes,
charges. So
yes.
already it is
So
dielectric material. For example, rubber you can take. So how is it is possible to create polarization there logically? Mathematically, I understood that
so
all
there'll
equation.
be an extent of polarization. So how much it will be depends on these factors that you are talking about, right? There comes the factor of susceptibility of the material. So depending
Yeah.
on the kind of, like,
Okay.
the kind of insulation that is there in the material, or
Hmm.
how tightly the charges are bound, the susceptibility will change. Okay. So but conceptually, there'll be a level of polarization.
Typically, what is the order of polarization, madam? For how much it is?
Uh, for rubber,
No, not for rubber. Like typical order of polarization. It is 10 power minus 20 or something like. Which
one
material is
second.
having more polarization, madam?
So, like I currently am not getting any example. One second, I'll just search and tell you. But basically, metals. So if you talk about metals, metals will have infinite,
Oh,
like dielectric constant will be infinity for that, right?
okay.
Like epsilon r will. So now it depends on where your material lies in that scale. So typical value of susceptibility, suppose. One second.
Okay.
Just interesting question. Like, because I have also never looked for the values. I'll just, maybe I'll.
Every time when I study mathematically, I'm compromising, but logically, I'm getting a doubt. How it in the space also everywhere field is there, madam. So because of that field, the materials in the space which existing, do they get polarized? Everywhere
So
field is there in the space. So polarization
epsilon
means
naught.
by the application of electric field and a dielectric atom, separation of polarities get be done. Because of that, some we are deriving mathematical equation of polarization. So that boosts the dielectric like flux density. Flux density equal to epsilon naught
Will
E
be
plus
changed.
some polarization. What is the
So
benefit of polarization, madam?
benefit, it's not about benefit, it's a property of the material. So basically, what is happening is, see, the effective field will be reduced, right? So if you keep a dielectric material in an electric field, so
Okay.
in a metal, so if you keep a metal in a electric field, the net field inside is zero. Now for a dielectric, what will happen? That you will have a effect, you will have a field inside, but that field will not be same as the applied field. That field will be reduced because
Oh,
of the induction of the charges, right? Now this induction is a measure of the dielectric constant or the susceptibility. So if it is polarized very well, if
hmm,
it has a large polarizability, then it would cancel the effective field, the applied field, to a larger extent. If the polarizability is less,
hmm.
suppose it's not able to polarize much, so in that case, what will happen is your field will not get cancelled to that extent, right? So
Oh,
in that case, your effective, like, basically, it's like, if you have a medium, now you have some field, how will that applied field result in a net field in that medium? So the field
Exactly.
in water and or the field in some material will be different from the field in air.
Okay.
That is that's the idea. Like basically, in air you have a certain kind of polarizability because there'll be some redistribution. In so in a metal there'll be a certain kind of redistribution. In every
So
medium there'll be a extent of
susceptibility is the
redistribution.
key factor here. Susceptibility is the key factor here. Right, ma'am? That for
Susceptibility,
polarization.
yes, susceptibility is the you can say the proportionality constant that relates that if you have a net electric field E, how
Hmm.
much is the polarization? That is
Yes.
that the so it might not be, so it's an approximation, right? The susceptibility expression chi, like normally we are considering it to be a scalar quantity, but
Yes.
it can actually be dependent on direction. It can have like higher order terms. It can have all these things. So this approximation that P is equal to something into electric field is an approximation in a way. You can also have E square terms, like in a more general point of view. But from a linear like perspective, in the linear regime, we consider that the polarization is affected by the effective field that you have, and that proportionality constant is your susceptibility. If susceptibility is more, there'll be more polarization. More polarization of charge meaning that the effective field will get cancelled more, right? If
Okay.
so that's the physical way of understanding. Here it says that the magnetic susceptibility of rubber is in the range of 10 to the power minus 5.
10 to the power of minus 5 coulomb per meter square, right, man? Yeah,
Uh,
polarization units are coulomb per meter square only.
Polarization unit will be okay.
Same as
So
D bar.
yeah, yeah.
Yeah, coulomb per meter square. Okay.
So this is in
And,
CGS. So CGS. So it should be in like centimeter units.
okay. And there are some, I heard materials like polarized atoms, non-polarized atoms. Polarization in polarized atoms, polarization in unpolarized atoms. Like H2O is a
Okay. Okay. So that is like your molecule or material itself has a net moment already.
okay. Yeah, yeah.
So understood, right? One is it. So it's like so like ferromagnetic and paramagnetic.
Hmm.
So in paramagnetic, what happens? In like just an example. So in paramagnetic, what happens? There is no field magnetization in the material, but when
Yes.
you apply, when it is in presence of some magnetic material, it gets
Hmm.
induced. But
Hmm.
a ferromagnetic material will always have a net magnetization, right? So similar to that, you can have molecules which are already polarized.
So, hmm.
And on the other hand, you can have molecules which are not normally polarized, but when you bring it in presence of some effective field, it gets polarized. So that's the difference.
Okay. Thank you. Thank you, madam.
Yeah. Thank you. Uh, so let's call it a day for today. We'll again meet next Tuesday. Thank you.
Yeah, thank. Today I learned a new concept like discontinuity of electric field from Gauss law. Inside the bulk, no field. That I before that I didn't know that, madam.
Oh, okay. Nice that you got to know
This
something new. So
capacitor
there's this very
stability will study, but that
Mhm.
concept learned very.
Yeah, so the very idea of caging, like the caging of electric fields, if you look for that, you'll see that. So basically, if you have some metal and inside that, if you keep a charge, it will actually be caged from the outside field. That
Yes,
comes
yes,
from this idea that the field inside a conductor is zero.
yes, yes. Thank you so
Okay.
much.
Yeah. Thank you.